Let's see. Okay, after reloading the page, it seems to be receiving the video. So moving on with the component placement of this motor controller schematic that I've designed here. And the main goal right now is to untangle this mess and to do it in the best way possible. So basically what I do is just go over every single component and I try to place things such that there is enough room for routing and such that I can route things in the best way possible. So for example, here I've laid out the EtherCAT part, and I placed the capacitors in between the capacitors and the space there, and then to the Ethernet connector here. So let's see what else we can do now here as the next step. Encoder interface. So I got two encoder interfaces because I have two motor drivers on this schematic, and these encoder interfaces are designed to accept plus minus 40 volts on the inputs, and they can also detect faults in the wiring. So it's kind of a smart encoder interface. This is the first time I'm evaluating this encoder interface, so it's going to be interesting to see how well it works. Let's see. What is the best place to put this? Let's see. Maybe something like this. Yeah, this seems reasonable. So I can select the whole thing then and rotate it like that. So the things that cross here are, okay, that one is not, yeah, that one's going there. So these two. Yeah, actually, a lot of them cross, besides these two. Okay, so we have that one there. Okay, this is not going to be a problem because this goes just around this chip and in there, and then this one goes around there. But here we have this one, yeah, this is going to be fine. And then we have just the 5 volts and ground. So this is fine. Next we have this connector here. I'm going to try to place all of the connectors that belong to each motor close together because I want, I think it's probably going to be such that I have one motor on one side of the PCB and the other one on the other side of the PCB. So all of the connectors that belong to one motor go to one side of the PCB and the other half goes to the other side of the PCB. But we'll see. Okay, so this is going to be something like that, and what I'll have to do here is just make sure that that I modify both of these footprints such that the connector is sticking out roughly 5 millimeters outside of the PCB. But first I'm going to move all of the footprints in place. So this goes there and this goes there. It looks like there is no way to avoid putting a few vias in order to make sure that all the pins connect properly. Ideally, I try to place components in such a way that as few pins as possible, or as few traces as possible cross, so that I can just route them on the same layer. But sometimes it's not possible. Sometimes I adjust the pinouts of certain connectors to make it possible, but other times I just have to live with it. Okay. So I have a feeling here that all of these connectors are going to be taking a lot of space. So we'll see what we end up with. We've got quite a few connectors. Like there are button connectors there, for example, and LED connectors. These connectors are they're designed like they're designed to accept plugs with screw terminals, which makes it very easy to connect external components or external wires to these connectors. So you basically plug in you plug in the wire into a screw terminal, and then you have a plug which you can just take out if you need to disconnect the connection. Okay. And then we have the filtering capacitor here, or 3 of them, which will all go somewhere here. Let's first get the resistor as well. Let's zoom in here. It's better. So moving, I'm just going to place them in the right. I'm just going to place them close together, and then I'm going to place them properly after I've moved all of them into the same area. Let's see. Got that one and that one. Capacitor. And the diode. Let's see. And then we have all of these bypass capacitors for the power that goes to the connectors. 2.2 microfarads. No, not the pin. Let's see. Yeah. And then we have 2 bypass capacitors here as well. So these seem to be in place. This one is probably somewhere there. Yeah. Okay. So let's zoom in here. And now we have this capacitor here. That's going to the A phase, and it's going to be connected. Let's see. All right. So the A phase is there. So this one can go here, and this one is the resistor, the corresponding resistor. And let's move them out a little bit so that we have enough space for the designator. And this capacitor is, which one? Yeah, this one is the bypass capacitor that goes here to pin 22. Pin 22 is there. I think we should just move it like this. should rotate it a little bit, by 90 degrees. Rotating the parts like this, I feel is better, because then I have more space to route out the other pins around it. So I try to keep as much free space as possible around the chip to account for the routing. Actually, in fact, I think it's better to move it a little bit out to get a little bit more space for these two pins. Next is this one. This is the B. Let's move this out for now. And this is the C phase, or the C signal. Or actually the Z, not the C. The Z signal gives the index pulse. It's delivered once per revolution in an encoder, and it tells you when the encoder makes a revolution. Let's see. Remove the designators there. And the diode goes somewhere here. Ideally, I should have probably been able to use a smaller diode, but because I'm using the BAT54 diode in other places, I try to reuse as many components as possible, which means that I will use this diode for this application here, for this particular use case. So the reason for this diode is to connect a push-pull output of this chip to an open drain output, and to make sure that the push-pull output doesn't get shorted by the open drain output if both of them go low. Or actually no, if the open drain output goes low and the push-pull output goes high, in that case I want to avoid the short, and this diode helps avoid the short in that case. The cathode has to go to pin 17. So it's kind of like this. I suppose we could just put it here. Let's put it here for now. Right, C74. This one goes here. And C75 goes to the next one. And let's see, C76 goes to the last one. Something like that. And what is this? C73, that's supposed to be here. All right. Anything else here? C61. That'll be the bypass capacitor that goes to pin 27. Pin 27. There. So all of the bypass capacitors have to go close to the power pins, because their main purpose is to provide extra current when the internal circuitry of a chip is switching. So they have to be very close to the power pins in order to do their job properly. And what that helps with is minimizing the voltage ripple on the main power lines, because the extra current comes from the capacitors and not from the voltage source. Okay, so where would be a good place for this chip? Here maybe? Something like that for now. All of these connectors belong to one of the motors, so I'm going to place them together. I have two motor drivers. Let's see, this one is number 1, and I think this one is, yes, this one is number 1 as well. Let's just move these parts out a little bit. So these ones are all belonging to motor number 1. I can move this block here. So somehow I have to come up with a good placement so that I have enough space for all of the connectors. And I'm thinking to kind of have one set of connectors on one side of the PCB, or on one edge, and the connectors for the other motor on the opposite edge. But we'll see how that works. I have to untangle a bit more of this mess first. Let's see what we can do next. We can do the LEDs actually, because 4 of these connectors are going to go on one side of the PCB and 4 will go on the other. And this is LEDs for the buttons. So I have a button interface as well, and there are buttons that come with LEDs, and the main purpose of this LED driver is to illuminate the buttons. So you can give sort of feedback to the user, certain dimming lights, dimming patterns. This is a very flexible LED driver and it's pretty cheap. Let's see here. Let's place all of these connectors. See how much space they take. I'm going to just place them close to doing a final placement, because I'm going to combine them with the button connectors. So it's going to be one LED connector and one button connector side by side. So this is kind of going to be like this. And yes, they take a lot of space, but they provide screw terminals in the form of plugs, which is very useful. But then, of course, if this results in absolutely unreasonable size of the PCB because of the size of these connectors, then I'll have to find a different solution. Okay, so the charge pump capacitors. These capacitors are used to drive the charge pump of this LED driver, which then generates the higher voltage for the LEDs. I think it's 4.5 volts for the LEDs or something, according to the datasheet. And the second one is over there by the chip. Let's see, is this? Yeah. So the way this thing is wired is pretty weird. It's almost that I have to check the actual pinout, if the pinout is correct, because having these pins like this seems wrong. It will be more reasonable if 23 and 24 were connected to one capacitor, so I have to check the datasheet. Let's see here. Yeah, so I didn't get any datasheet there. I'm gonna open up the component. I have the fields loaded automatically from the online API. So I just provide the product code in my library, and then I load the fields automatically. So I get things like how much I have in stock, and or yeah, how much the supplier has in stock and stuff. But let's see. Let's copy this and go to Mouser and see if we can find the datasheet for this chip. And I'm going to ensure that the charge pump capacitor pins are correct, because I already checked that, but still it seems strange to me that they're placed in such a stupid way. Component placement is kind of like solving a puzzle. You try to move things around until it makes sense. So where pin configuration and functions here. Could this datasheet actually be wrong? Like sometimes datasheets are wrong. It seems that 23 and 24 is the negative. That one is positive. Application schematic. Let's see. Implementation. The layout. Maybe I can see the layout. Okay. So because they made a stupid package with stupid pinout, they have to do this kind of shit to make it work. Oh, amazing. Okay, so it seems that this is correct indeed, but it's certainly not the most. It's certainly not the smartest way to wire this chip. I'll select all, and in the datasheet they basically place the capacitors like this. Okay. 10 microfarad capacitor there. So in the datasheet also they use smaller capacitors, but since I reuse parts in this schematic, the parts that I use elsewhere in the schematic, I may have different size of the capacitors, like different physical size. And sometimes also different capacitances, depending on what makes sense. Alright, although there was another capacitor, I think. What was this? This was V out. Let's see. The V out, yeah, this one. All right. And then I want to just place this as well. So this is a hardware button debouncer. Okay, I'm just going to place them. Make sure that they're in one place before I place them. Fine. I think that there are several improvements that KiCad can make to the way they do workflow that will significantly improve the effectiveness of working in KiCad. For example, just things like this, where I have to, I click on the schematic and then I have to click to select this window. It would have been nice if I just had to, if everything was in a single window, and I could just move the mouse to the other half of the window, and automatically get focus on that half of the window. Let's see. Okay, and before I do any proper placement of these components here, I want to just get a feel of how much space all of this stuff is going to take. So there are a few more things that I want to just place very roughly to get an idea of how much I need to account for, how much space I need to have on each side of the PCB. So that's that one, and this is This is a digital potentiometer that outputs a voltage. So this is a digital potentiometer that connects to op-amp chip, and the op-amp chip then outputs a voltage on the output connectors here. And this can, the idea here is that this can simulate a joystick output. So it doesn't have to be fast. It's kind of like a digital to analog converter, but a slow one. So you set the resistance of this digital potentiometer over I2C, and then you get the voltage output here with low output impedance. The biggest benefit of just moving things into one place is that I can then click on them in the layout view and have them selected in the schematic, and then I can just do more precise placement without having to zoom in and out all the time. Yeah, this one was there. Okay. This capacitor goes there, and this capacitor. Let's see. This capacitor goes to the op-amp. And then I have this, the joystick input here. Let's see. It would also be very nice if I could zoom in based on, by selecting an area. So if I could just press some key and then just zoom in. Let's see here, is this impossible now? Zoom to selection actually, yeah. Maybe this is possible. Maybe I can do like this. And how exactly is this supposed to work? If I select more components, more than just one component, is there like zoom to fit maybe? Nope. Damn it. Okay. So it doesn't seem to be possible to zoom in to selection of multiple components. I don't know. Maybe somebody knows how to do it. Feel free to comment on the video. Okay. So let's move this commode out there, and the multiplexer. and then set the power as well. I think that by far the best KiCad workflow tip for accelerating development and making sure that there's less bugs in the schematic is to have a custom library. So you basically consider all of the components in the KiCad libraries as templates. So you use them to create your own library, just so that you don't have to sort of recreate the shapes of op-amps and things like that. Let's see. Okay. No way. You gotta be kidding me. Okay. So the no fit. I started using, on the schematic, I started using kind of like a comment to signal a no fit. But it seems that this didn't even come into the PCB. So this will need to be changed. Anyway, let's continue with all the other components here. But having this custom library where you have parts named like res something for resistor, IC something for chip, and then you have product codes connected to these parts in the library. So you can assign footprints once, and you can assign product codes. You can double check that everything is correct, and then you reuse that component on the schematic. Instead of following this standard ridiculous workflow that has been in KiCad from the beginning, where you assign values as fields, like you place generic components and then you assign values, and then by the end, when you are done with the schematic, the idea is that you're supposed to assign the footprints. I think that is a ridiculous idea, because doing that right and doing that right every single time is close to impossible. I'm gonna have to check how KiCad actually implements this this commenting, and maybe I can just change it so that so that the footprint is placed on the PCB, but does not appear in BOM or something like that. Let's see. All right, let's do a bit better placement here. Come on. Got R5. I'm going to align these connectors with a middle pin. So in KiCad, depending on which pin you're closest to with the cursor, when you press move, it's going to align that pin to the grid. Let's see, P15, P14, P13, let's move R6 in place as well. The purpose of this diodes is to clamp the input at 5 volts. Right, R14, yeah, it's probably R22. Could it be R22? Let's see, yeah. Okay, I got the D7 there as well, so to find R8. My dog seems to be throwing up. That's not good. Maybe she has eaten something. Maybe it's bits and pieces of the sticks that she plays with. Seems to be okay now. I'm gonna keep an eye on her. She doesn't usually swallow sticks when she plays with sticks. Like when she plays with a stick and then she kind of starts breaking off pieces of the stick, she doesn't usually swallow them. So it's mostly just that she breaks up the stick. But sometimes I think she gets smaller pieces swallowed, and then she throws them up, which I try to avoid. I try to prevent her from chewing on sticks. Seems to be fine now. Okay. Let's see. Right, so this is going to be the bypass capacitors for the connectors here. So there's going to be one capacitor per connector and per power rail on the connector. Do I have all of them? No, there's another one there. Let's place this one. So I can place them like that, and then I can select, let's see, I can select all of the parts that I can select all of the resistors and capacitors. Let's see if this works. No, too little. Let's make a little wider selection. There we go. And I can see that one is missing there, but I can find it in a bit. And then I can just do align distribute and align right. And I get all of them aligned. There is another one that's missing. There. I actually want to move these ones out a little bit, like that. And then I'm going to align all of the diodes as well. Let's see. And I'm going to align them to the left so that I have a little bit of space there, but I think I can also move them closer here as well. Okay. Let's see. R17 has to go to pin 13 on the op-amp chip. Pin 13. Oh, there is another op-amp chip, of course, because there are 4 of them in each physical package. So that means we have 2 op-amp chips. Let's see. not bleed. Come. Come. Come, Alice. Come. Come. Alice is awake now, and Alice needs to go out and go to the toilet. Alice is my dog, which you can see in the other YouTube videos that I have on my channel. So I'm gonna take a small break. I'm gonna take her out to go to the toilet, and then I can continue. Thanks for watching, and I hope you learned something.